Well, everyone, the two of you. Okay, so conditional statements. All of our theorems, if you've noticed, have been written in the form called a conditional. If something, then something. The part of the statement after if is called a hypothesis, and the part of the statement after then is called a conclusion. So the way we've been writing our theorems is if something, then something. If the hypothesis, what we think is going to happen, then we have a conclusion. Example, not a mathematical one, but if today is October 31st, then today is Halloween. Our hypothesis is today is October 31st. Our conclusion is today is Halloween. That's a true statement. The converse of a given conditional is formed by switching the hypothesis and conclusion, switching them. So if I put today is Halloween here first, today is October 31st after then, I get if today is Halloween, then today is October 31st. That is also a true statement. Not writing for me, but that's true, and that's true. So both pieces are true. The statement that we made and its converse. When both the original and its converse are true, it's called a biconditional statement. Biconditionals, sometimes written if and only if. I've used those before, that term. If and only if. Today is October 31st, if and only if today is Halloween, or IFF. The converse is not always true. Not always true. For the most part, what we deal with will be true, but it's not always true. Let's look at this one. If you live in Haverstraw, then you live in New York. There's our hypothesis. Go green. There's our hypothesis. There's our conclusion. That is true. Well, relatively true. There could be a Haverstraw somewhere else, but for our purposes, it's true. However, if I switch the if and then, if you live in New York, then you live in Haverstraw, that is not always true. You can live in Stony Point. You can live in Pomona. You can live in Westchester somewhere, anywhere in New York. So that's why the converse isn't always true. For all intents and purposes, the theorems I give you, and if I tell you there's a converse, it will be true. So let's look at about the converses of each of our conditional statements, right? We had the corresponding angles theorem. If two parallel lines are cut by a transversal, then the pairs of corresponding angles are congruent, right? That's what this diagram says. If these are parallel, then these two angles are congruent. Well, how would I write the converse of that? I have to take this then piece, right? Everything after then from here on, and put it first, and then the parallel lines part second. Now be careful. Sometimes the wording gets a little weird. You have to be careful how you word things. So the converse of the corresponding angles theorem would be, where'd it go? Oh, come on, it showed up before. Ay, don't know why it's not showing up now, but that's okay. It is what it is. All right, I guess I'm going to have to write it out. If the pairs of corresponding angles, if I want to write in red, I want to write in, 36. Let's make it 28. Doesn't matter if it's red. If the pairs of corresponding angles are congruent, then the two lines cut by a transversal are parallel. Right. So it's just slightly different. I didn't take two lines cut by a transversal and then the pairs of corresponding angles are congruent. I You got to kind of word this correctly. So if the pairs of corresponding angles are congruent, so if I know this part is true, right? That's all this is saying. If I know that this is true, if I have this already, then I know I have parallel lines. That's all the converse says. If the pairs of angles are congruent, then we have parallel lines. If we have parallel lines, then the two angles, corresponding angles, are congruent. Two parallel lines are cut by a transversal if and only if the pairs of corresponding angles are congruent. So the converse is just be careful of the wording. It'll be in here the way it's supposed to be worded. I had it before, and I don't know why it's not showing out. So we have a converse for the alternate interior angles theorem as well. And of course, that one doesn't show up. So if alternate interior angles are congruent, if alternate interior angles are congruent, then the two lines cut by a transversal are parallel. Right? So we can form the converse from all of these. All this is saying is if we know alternate interior angles are congruent, then we know the two lines are parallel. If the lines are parallel, then the alternate interior angles are congruent. Same thing goes for the alternate exterior angles theorem. If the pairs of alternate exterior angles are congruent, then the two lines cut by a transversal are parallel. I'm not going to write this one out. This was supposed to come up. It didn't. You can, oh, wait a minute. Maybe if I did this, look at that. That's why. Ah. So if alternate exterior angles are congruent, then the two lines cut by a transversal are parallel. That's what I had to do on the other one. Didn't realize it. Let me just go back so that when I clear ink, oops, undo, undo. Yep, I know. We got there, we got there. So if I take this and I delete it, and then take my eraser, and look at that. All right, this is just for you guys here in class. You're going to get this when I send it home too. So it's written out nicely instead of the way I did it. And this one as well. It kind of says the same thing, but I'd rather have it nice and printed out the way I meant it to be. There you go. If alternate interior angles are congruent, etc. Converse here. So the converse to the alternate exterior angles theorem. If alternate exterior angles are congruent, then the two lines are parallel. Right? The converses just tell us consecutive interior. We know that when two parallel lines are cut by a transversal, the consecutive same side interior angles are supplementary. So the converse will be slightly different. Let's see if I can do this. There we go. If same side consecutive interior angles are supplementary, then the two lines cut by a transversal are parallel. I hope you're getting the idea of this. If two parallel lines are cut by a transversal, then the pairs of consecutive exterior angles are supplementary. This is the one that wasn't in your book, the one that I gave you. So the converse would be, if the same side exterior angles are supplementary, right? I don't have a picture for this one, then the two lines cut by a transversal are parallel. I have them written out. It's theorem 3.5 in your book. I just wrote them out for you. All right, so let's see if we can use these converses. Find the value of x that makes m and n parallel. Well, these two angles are what kind of angles? They're corresponding angles. So when the corresponding angles are congruent, when these two angles are congruent, then these two lines will be parallel. So in order to find the value of x that makes them congruent, we set these two things equal to each other. 3x plus 5 equals 65. 3x equals 60. I subtracted 5 from both sides. Divide by 3. X is 20. So when x equals 20, these two lines will be parallel because 3 times 20 is 60 plus 5 is 65. These will then be congruent angles, congruent corresponding angles. If congruent corresponding angles, if you have that, then you have parallel lines. Explain. Is there enough information in the diagram to conclude that these are parallel? Well, what kind of angles do we have? These are same side exterior angles. So if these two angles were supplementary, then these two lines would be parallel by the converse of the same side exterior angles theorem. So let me go to pen and I'll write in blue. Let's call it angle, I'll write it red. Call this angle 1 and angle 2. If angle 1 and angle 2 are supplementary, then M will be parallel to N. Are they supplementary? What does angle 1 plus angle 2 equal? So let's see. Angle 1 plus angle 2 equals 180, right? That's a question mark. If that's true, then they're parallel. 75 plus 105, does that equal 180? 180 equals 180. So yes, those two lines are parallel because the same side exterior angles are supplementary. And here's a page with all the theorems on it as well. When I send this home, you can write those down, put them in your notebooks, have them somewhere, somehow. The transitive property of parallel lines. We didn't talk about the transitive property. Transitive property just says that if A equals B and B equals C, then we can go right to A equals C. Transitive just means if two things equal the same thing, they're equal to each other. Well, if two lines are parallel to the same line, then they must be parallel to each other. If P, this one here, let me go to red. If P is parallel to Q, right, and Q is parallel to R, then I know that P, which is the same drawing I just made, is parallel to R. And that comes in here. P is parallel to Q, which is what we just were showing. So P is parallel to Q. And Q is parallel to R. So all three lines are parallel. We can ignore kind of this one in the middle. Now these two angles have to be same side exterior angles. So they must be supplementary. So 180 minus 115 is angle 8 equals 65 degrees. Exercises 21 to 24 are AC and DF parallel. So we're trying to figure out if AC, let's see, do I want lines? Yeah, why not? Let's do red and make them a little bit thicker like that. Okay. So we want to know if AC and DF are parallel. Well, if they were parallel, right, we have one transversal here and one transversal here. Do we have enough information to say that they are parallel? Well, a couple of things we can do. This is a vertical angle in here, right? Or corresponding, but we don't know anything else about them. So we're going to have to use that vertical angle right here, right? That angle there also has to be 115, right? That's the vertical angle theorem. But if that's 115, if these were parallel, then these two angles would be supplementary. 115 plus 65 is equal to 180. So yes, these are parallel. Explaining your reasoning is the words I just used. Because angle EBC is 115 by vertical angles, and because angle EBC plus angle BEF equals 180 and are supplementary, then by the converse of the same side, interior angles theorem, those two angles are congruent. Those two lines are parallel. All right, so to prove that lines are parallel, we need the converse of one of the four theorems we have. This will be your homework. I will send that to you on Classroom as well. And for you in the class, I'll send that in a minute. But right now, I want to stop recording. And